Hello everybody and welcome back to the lecture on computer graphics. In the last lecture we had been discussing about CRT displays and CRT monitors and specifically the refresh raster displays. Okay. And today we will continue on that and try to wind up the discussion on CRT displays. And the three main concepts with respect to the refresh raster displays, which is a point plotting device unlike the line drawing or stroked displays, vector displays of random scan or DVST, is that we basically draw points and we have to worry about video rates, refresh scan rate, number of lines, time regarding vertical retrace, horizontal retrace. We talk of interlaced fields. We also talked about the bandwidth about accessing a pixel, the time for accessing a pixel to switch on and switch off the beam, controlling the beam. We talked about architectures, and finally we also discussed about the direct relationship between the frame buffer, memory, array of pixels and the spots on the screen. So, if we look back into the last slide which we discussed in the last class, we were talking about a n bit plain gray level frame buffer, n bit plain gray level frame buffer. So, we visualize that a bit plane is a single bit. So, there are n such bits stacked, and for corresponding to each pixel there are n bits, or typically it could be 1 byte if n is equal to 8, and the contents, corresponding contents of that bits from those n bit planes are stacked parallelly loaded onto an n bit register, which fires a 2 to the power n DAC, a digital to analog converter, which generates a corresponding voltage proportional to the digital value at the register, and the electronic gun gets that input and controls the strength of the electron beam, which will go and strike the corresponding dot on the screen. Of course, we do not have to worry here about the deflection voltages generated by the video controller automatically as the beam is being scanned left to right and keeps going down with horizontal retrace, and then of course even and out fields, vertical retrace, diagonal retrace, all that is done automatically. And at the same time, at a given instant of time, when the deflection voltages, the horizontal and vertical deflection voltages allow the beam to strike at a particular point, corresponding to that the intensity of that pixel is being taken out from the frame buffer and loaded onto a register, which in turn goes to the DAC and fires the electron beam. Okay. Now, we have been talking about n bit, n equal to 3, 8, various configuration, bit plane when n is equal to 1, we have black and white. What about color? So, when we talk about color, we go to the next slide from here. A simple color frame buffer can be done with n equal to 3. We talked about this in the last class, that to implement a color, we can't do this with a single gun. We need 3 separate guns for the 3 fundamental color. We are talking of an RGB representation of a colored image. There are of course other representations which we will talk later on in the lecture about color models and color representation, but here we take just n equal to 3. That means we are assigning just a single bit for an individual color. The red color has a single bit plane, the R and the G and the B also for the green and the blue. Henceforth, we will talk of RGB as red, green, blue, respectively a single bit plane for each individual color. So, if you look into the monitor now, the screen shows that there are 3 such bit planes, and the corresponding we assume here that the corresponding bit values 0 or 1 only in this case is been taken out from the frame buffer, load onto a 1 bit register, which in fact fires a DAC. The digital to analog converter will convert that bit value into a corresponding voltage 0 or some non-zero value, and the corresponding color guns. Now, we have these 3 color guns. We have been talking about 1 color gun so far. Now, the first time we are going to have 3 color guns separately for the 3 colors or 3 channels of visibility. You can visualize R, green and blue, and what is done basically, all the beams correspondingly from all the 3 guns simultaneously are fired onto 1 pixel point, and this pixel should also have 3 dots respectively for R, G and B, and they will receive the corresponding intensities of the guns and illuminate a pixel which will appear as color. Okay. The CRT raster will have the same resolution as the frame buffer, but each pixel has 3 dots. That is the significant difference. We will look into that as we go along, but before that, if we just use n equal to 3, then n bit plane gray level frame buffer. In case of just 1 bit, for each color frame buffer we get 8 colors. Now, if you are used to truth tables for n equal to 3, there are 8 possible values which one can hold in the frame buffer at each pixel position. So, we correspondingly have 8 different colors, and this table shows the corresponding values of red, green and blue. The first row talks about red, green and blue, all 3 zeros, and we have the black color, which is of course very obvious because none of the electronic guns are firing with an intensity. The beam is switched off and the pixels also do not grow. So, we have black, and at the bottom of the row, when all of them burn simultaneously and hits the corresponding 3 pixels, you have the white color. Okay? And in between you have other variations, of course, the pure blue and the green and the red corresponding to 001, 010 and 100, the truth table for RGB respectively, and other mixtures of 011 will create a cyan, and a 101 will create a magenta. I have labeled the corresponding color with the color value itself, so that it gives you an idea. Very nice illustration, and red green combination together 11 gives you the yellow color. So, you typically can have 8 colors using just 3 n equal to 3 3-bit planes, and this sort of getting 8 colors display was traditionally called an EGR extended graphics adapter card, which is to provide with an EGA display. Okay. Well, we were talking about 3 dots on the screen which are to be fired by 3 different guns, and this shows how it is implemented. Okay. So, we are talking of an operation of what is called a delta-delta shadow mask CRT, and 3 electronic guns aligned with a triangular colored dot patterns on the screen are directed to each dot triangle by a shadow mask. Okay. So, the beams from the 3 electron guns, which are also arranged in some triangular arrangement as like the colored dot patterns on the screen, and the beams come out. The respective guns, as you can see on the left hand side of the screen, R, G and B will emit correspondingly beams which are sensitive to R, G and B respectively, and they actually pass through a shadow mask which allows the beam to pass through only that dot and hit the screen. The shadow mask arrangement does not allow beams to go at any arbitrary angle and hit the screen. It is specifically aligned with the corresponding arrangement of what I will call as the magnified phosphor dot triangle, magnified for you to see it, otherwise almost is not visible to the naked eye. You might use a lens and come very close to a CRT monitor to see each individual dots. That may be possible, but not visible to the naked eye. So, it has been zoomed and shown separately that is a typical arrangement, a triangular arrangement of the 3 phosphor dot triangles, and they respectively are sensitive to the color of the electron beam which is now fired by the respective guns. Okay. So, that is very, very important, RGB, and of course, the screen is full of such dots. So, selection of shadow mask is very important, and the beams actually converge at the center of the shadow mask and then cross over and hit the screen. Okay. This is probably a better arrangement to show what actually was being meant in the previous diagram. In terms of it, we have enlarged the shadow mask and also the CRT face. We are talking of a colored CRT electron gun and a shadow mask arrangement for a colored CRT screen. So, left hand side the beam comes from the electron guns. Those guns are assumed to be there, but is not shown from the left hand side. We have the green beam, the blue beam and the red beam coming out from the respective electron guns. They intersect, the beams converge at the perforation. This is basically a perforated sheet, so like a filter is what you can, but it is metallic. The shadow mask is typically metallic. A perforated sheet type of thing is what you can imagine, which has perforations or holes through which the beams are allowed to pass, not arbitrarily anywhere, and the beams converge there. Of course, nothing happens, it just emanates out in a triangular arrangement once again, and they will go and hit the corresponding red, green and blue phosphor dots on the CRT face as marked on the right hand side of the figure. The dashed arrow shows the corresponding dots on the screen as R, G and B. Do not mistake yourself to visualize that the beam passes through the CRT phase and goes towards the letters R, G and B. No, just they are the markers shown. Those are the, in this case the top one is the R and the right is the blue and the bottom one is the green respectively, as the beams converge out of the shadow mask and hit the corresponding phosphor dots on the screen. So, I think this is an arrangement which shows you how this is done. But if you look at the CRT face itself, If you look at the CRT face and how the triangular arrangements keep going, basically what it means is that we have a phosphor dot pattern of a shadow mask CRT, and this is a CRT. Of course, the shadow mask is in front of you, do not worry about that, but the corresponding beams, the RG and B, they come out of the shadow mask and hit those corresponding pixels which are shown by the color, and then we have these it's shown by a circle. So, that circle is one such circle is a phosphor dot pattern, a phosphor dot basically, and 3 of them form a triangle. So, there are 3 triangles shown, the top 2 corresponding to the scan line number 1, let us say, or the top scan line, and similarly at the bottom we have another scan line which is also going, and the RGB alternates basically. Okay. So, the same G could be used for the next one and so on. So, the beams have to be changed as you go along. The PRG arrangement could becomes basically in the next pixel RGB and so on. So, this is how you probably save space. Otherwise, if you have to have separate triangles, non-overlapping dots, the CRT have to be very large, and you cannot make it very compact and high resolution within a particular dimension, so that you have a continuous picture. Otherwise, if you have large dots separated, you do not have a very continuous feeling about the picture. So, for a very high resolution CRT, this is a typical arrangement of the phosphor dot pattern, okay, on this screen. Okay, continuing with the n-bit plane gray level frame buffer, we will come into more illustrations and pictures, but just a few points regarding the bit planes and the colors. Typically 8-bit planes per color is used. Okay. So, if you want to have full color for R, G and B separately, we talked about 3 colors each individual bit plane, but typically, and we also talked about n-bit plane gray level. So, why not have the n equal to 8-bit plane for each individual color. So, for R we can put 8 bits, okay, for G also 8 bits, and the blue B also 8 bits. Okay. So, together you need basically 24 bits, and a 24 bit plane frame buffer with 8 bit planes per color is also used. Okay. So, that is the typical arrangement which is desired, and each group of bit planes which form corresponding to one particular color, it basically drives now an 8-bit DAC. So, it is getting a bit complicated, but we will try to see. I will give an illustration of the entire figure somehow, because we talked about 1 bit plane, and then of course n equal to 8, and then 3 color guns with each bit plane per color, but not talking about 8 bit planes per color. The 24 bit planes have to be put inside the video controller as well as in the monitor to drive, to be driven by the video controller. Okay. Each group generates now 256 shades of intensities of red, green and blue. That means you have 256 shades of red corresponding to dark and very red, and similarly you can have 256 shades of green and as well as 256 shades of blue, and these are each group which could generate that. Group means we are talking about the 8-bit planes corresponding to a group, and then an 8-bit register, and then a corresponding DAC which will be fired by the register to generate different color beam intensities corresponding to different shades of colors. Okay. So, typically if you look at this, we talked of 2 to the power 3 equal to 8, 2 to the power 8 equal to 256. Now, we are talking of 2 to the power 24 possible colors. That is a very, very large number of colors. We are talking of about 16 million almost, and that is the engineering standard which is used, 16 million colors, and this is called a full color frame buffer. 16 million colors are there at your disposal, and we call it as a full color frame buffer. Now, before I go on to the next slide, I must put a point here that I am sure that whether it is an artist or a graphics page designer or a web page designer, in no way can visualize, or even you can say that one doesn't need 16 million colors to draw any picture, however complex it is, how many sorts of colors you may need to display for a screen. Either you are talking of a map or a 3D diagram or simple lines and textures and things like that, you typically, I do not think you need more than a few hundred. Okay, few hundred colors are in fact quite sufficient for you to display any complicated picture. Of course, let us not go into algorithms about the selection of colors and all that. There are many such things existing, but what we are talking about 16 million colors, impossible to even visualize. To distinguish between 2 such colors, if I give you very adjacent ones just differing in 1 bit with red, green and blue, I do not think you can visualize. So, it is often necessary that the graphics designer or the artist, whomsoever you talk about, when an artist paints also with a color, he will make certain colors with again different shades on his canvas, and then use it to draw, and he probably does it with a few tens different types of colors and draw it in layers and phases. When we look at color shading, we will see there is a correspondingly a painter's algorithm being talked about, which uses the concept of what a painter does in terms of shading, but really you need more than few tens or few hundred couple of hundred colors, different colors to do that. So why do you need, we talk about 24-bit full color frame buffer, because it's also difficult to implement, you don't need that. So you will select a set of colors out of these, and how to do that? How to do that? We go to the next slide to see the complexity involved in a 24-bit full color frame buffer as given here. So we have 3 groups of 8 bit planes each for individually separate color. On the left hand side, then the frame buffer, you see the black colored frame buffers, groups of 8, each group of 8 bit planes for red, green and blue respectively. Okay. So the corresponding bit values are loaded onto the 8 bit registers, and this is a typical example. The zeros and ones are shown in binary, and the corresponding decimal value for blue equal to 75, you can check it out yourself. Green equals 172 and the red is equal to 10, 1010, that's 10. Is also displayed. So that means this is, we are going to display a particular point with a color intensity where the red component will be 10 out of 256. You can take a fraction of that. Green is 172 also out of 256 and 75 out of 256. Basically the programmer doesn't need to load values like this. It typically loads in a normalized range from 0 to 1. Okay, from 0 to 1, and the values are put onto the bit plane, and then it is automatically loaded onto the register, which again drives an 8-bit DAC. Now we need 3 8-bit DACs, 3 color guns, 3 8-bit registers, 24-bit plane. So that's a huge demand on the bandwidth and memory requirement, and these color guns will of course go and ignite that phosphor dot triangle on the screen to eliminate this color. Now yes, in this arrangement, if you have, typically you will have 16 million colors possible, but typically if you take a raster screen which is of a maximum resolution about few hundred by few hundred, or even take 1280 and by 1024 or 1700 and all that, we are talking of the order of about 10 to the power 6 or different pixels. And even if you let us say put each like a random dot colored pattern, each different color on the thing, you will not probably need 16 million colors, and that is stupid. You're not talking about trying to put a random dot color arrangement and show something. That's okay. So you need a different set of colors. You need definitely fixed set of colors to draw any arbitrary picture, and you don't need to worry about 2 to the power 24 colors. What will you select? Okay. So to handle the to make the life of the programmer easier, that he doesn't have to worry about 16 million colors which to choose from, we use a concept of what is called a lookup table within the frame buffer. Okay, just before the frame buffer sort of a thing. Okay, but it basically sits between the frame buffer and the registers. Okay, so lookup table or LUT or LUT as it is called, we talk of an n-bit plain gray level color frame buffer with W bit wide LUT or lookup table or LUT as it is called. There are different pronunciations, but I will use the word LUT correspondingly as given here, or a LUT. What this basically means, what does the LUT do? And typically the value of W is much more than N. Okay, typically that doesn't mean of course that if you are choosing a 24-bit plane, W goes more than that. That's not the key. Let us try to visualize what will happen if N is equal to 8. Okay, N equal to 8, try to visualize, and W could be more than 8. It could be 12, 16, 24, up to that. You don't need more than 24. So W could be 24 at the maximum. N less than W is what you have to visualize. The n-bit register which will load the contents of the frame buffer onto the n bits of the register, the content of that, that means the corresponding byte value which will come out of the register, that acts as an index. Okay, index, I hope you understand in terms of memory address, index to the lookup table. So you can visualize lookup table as a sort of sequence of memory positions, and how to address the corresponding position in the memory address depends upon the index pointed out by the register or from the lookup table, and that index will be used to access the corresponding contents of the lookup table. Okay. Thus, if we have this arrangement, we will put the figure now. Thus, out of 2 to the power W possible intensities, because the lookup table, if it is W bit wide, can hold obviously 2 to the power W possible values or 2 to the power W possible intensities, and that is what it's available. and out of that only 2 to the power n different intensities are usable at any point of time. Why? Because that is what will be loaded inside the frame buffer. The frame buffer is n bit wide, so you will have 2 to the power n possible values. The lookup table has 2 to the power w possible values. So you can at any given point of time choose 2 to the power n usable values out of 2 to the power w possible intensities. Remember, w is more than n, so 2 to the power w possible values is much larger than 2 to the power n values which can be loaded in the frame buffer, but you could choose which of those 2 to the power w intensities or values of color you would like to use and choose them and load the frame buffer. So this is why this is how the lookup table helps basically in helps the programmer to choose his colors efficiently and without bothering about a very large value. Okay. So that's what I was saying. The last point, the programmer must choose 2 to the power n different intensities based on his requirement and load the LUT or the lookup table, which is addressable position in memory, like we talked about frame buffer, which is addressable. The LUT is also addressable, and that has to be loaded before use. Okay. So that has to be loaded before use. Well, we look at the diagram of an n bit pen gray level frame buffer with a w bit wide lookup table. Okay. The overall arrangement in a simplistic situation, I have taken a simple example so that first of all the scenario looks simple and of course fitted on a particular screen itself. We are talking of an n bit frame buffer, n is equal to 3 simple case we have chosen. We remember we got the EGA 8 different colors possible. So now with 2 to the power 3 n 8 different possible intensities you can use, or the programmer can use. And the question is, he may need only 8, but which 8 out of many? I mean, he can choose 8 out of 2 to the power 24 or 16 million colors, but he is happy with the 8. He does not need more than 8 is what we assume. So the contents of the frame buffer are loaded onto a 3 bit wide register, and that register contents now act as a, you see a pointer to the lookup table from the register. From the register when n equal to 3 is written, there is a pointer to the lookup table. So the contents now, the value is let us say in this case 2. So 0, 1, 2. So it is pointing to the third row, starting from 0 the count 0, 1 and 2, it is pointing to the third row of the lookup table, which has a value 1, 0, 1, 1. What is that value? 8 plus 3 equals 11. That is okay, but what I mean is the contents of the register are acting as an index or a pointer to the lookup table entries, and the corresponding third row, the third content will be picked out from the lookup table, which is w bit wide. Now this is interesting. Register was 3 bit wide, 8 possible values, but w is 4 bit wide. So 2 to the power 4, or in fact you may have 2 to the power no, I'm sorry, out of 2 to the power 4 possible values, the lookup table number of entries will be only 2 to the power n, because that is what the register can access. The register with the 3 bit wide or n bit wide cannot access more than 2 to the power n entries, or 0 to 2 to the power n minus 1. So those means, so basically I have this lookup table with 8 entries, because n is equal to 3. 2 to the power 8, 2 to the power 3 is equal to 8, and 0 to 7. So there are 8 entries in this lookup table, but each is 4 bit wide. That is very interesting. Each is 4 bit wide, and this contents is 11, which is coming out from the third location pointed to by the register, and the lookup table output goes to 2 to the power w DAC. That is interesting. Now the DAC, instead of being 2 to the power n bit wide, is basically having capacity of 0 to 2 to the power n, will have different levels from 0 to 2 to the power w. So it has more number of capacity than what the frame buffer can access, and that is an advantage, because now 2 to the power 4 16. So out of 16 possible intensities, you choose your 8, that the programmer chooses his 8 possible intensities, whatever he needs for to draw his picture or color, and then loads the corresponding 8 positions of the lookup table with only those intensities. So the programmer apparently knows where is the color which he requires, in what position in the lookup table his desired color is, any desired color, 8 desired colors out of 16. So he chooses 8 out of 16, loads the lookup table with the corresponding 8 entries and access it by a register. So that picture I hope is very clear to you, and the lookup table output goes to 2 to the power w DAC, and the DAC gives a corresponding analog voltage intensity, analog voltage, let us say, which is proportional to the input to the DAC. So out of 16 possible values, he can although he gets in 8, but it has the capacity to give any output from 0 to 15 although there are 8 possible values. So, electron gun, of course, the CRT, the rest part of it is very simple. So, this is a typical arrangement. You hope you understand from the figure about an n bit plane, gray level frame buffer with a w bit wide lookup table. Previously, we did not use this lookup table. What would have happened without a lookup table? Yes, the n bit contents of the register would have directly gone to a 2 to the power n DAC. Directly from the register it would have been driven to a DAC, and you would have had a 2 to the power n DAC, and you would have had only 8 possible intensities, but fixed 8 intensities at any point of time, and that is what the electron gun is able to fire and what you can choose. Now, you can choose any 8 out of 16. In fact, increase W, take W equal to 8. If you take W equal to 8, what you are visualizing? Well, the size of the lookup table in terms of its content entries will be, could be still 8, that depends on the value n, which is 3, but you can now choose those 8 colors from 256 colors, because W is 8 bit wide. So, there are 256 possible color values or gray level intensities, and you can choose just 8 out of 256 and load the lookup table and address just the corresponding 8, and you will then use a 2 to the power W DAC, which needs, because the output will be a W bit wide from the lookup table. So, you need a 2 to the power W DAC, not 2 to the power n, to fire the electron gun. Okay. So, we are talking of 2 to the power W intensity levels, 2 to the power n at a time when W is more than n. If you look at the bottom left of your screen, that is just a comment which we are just discussing now. We are talking of 2 to the power W intensity levels, 2 to the power n at any given point of time. Now, if we can change the lookup table contents, those 2 to the power n which are accessible, those values could change. 2 to the power n, that number remains constant, but what the entries in the lookup table could get changed, and you can any given point, or you can have basically 2 pictures with 2 different lookup tables on a particular screen, having entirely 2 different set of colors chosen by the programmer. Okay. Now, the most complex scene is what we are looking at, a 24 bit plain color frame buffer with a 10 bit wide lookup table. Well, I can't put all that here, but what we are looking here is we are looking at n equal to 8, because 24 bit. So, 8 into 3 is 24, n bit wide, assume n equal to 8. So, we have a 24 bit plane, groups of 8 bit planes, as you can see on the left hand side, 1 for red, 1 for green, 1 for blue, and each is n bit wide. The contents are put to a horizontal register here. This is the register for red, that is the register for green, and that is the register for blue. Those registers are all n bit wide. In this case, again, since it is 24 bit plane, we are talking about n could be equal, n is equal to 8, but you can take even a typical case of n equal to 4. So, we are talking of about maybe 12 bit plane. Okay. So, does not matter. What it basically means is we are talking of n bit wide register, n in this case is 8, let us say. And then, so we have 2 to the power n entries for each color set for the frame buffer. Frame buffer, each group for each individual color, consider only R, only green, or only blue, any one of the 3 colors. We have n bit planes for R, let us say. We have an n bit register for the red, and the contents of the n bit register are fed as an entry to the lookup table. So, you are looking at any one out of the 256 possible entries in the lookup table, because 2 to the power n we have taken n to be 8. So, 2 to the power 8, 256 entries are there in the lookup table for each channel, similarly for red, similarly for green, similarly for W. That is an example of a color lookup table here, and one this is a lookup table for blue on the right hand side, middle we have a lookup table for green, and the left hand side bottom we have the lookup table for red. It is not necessary that W should be equal to n. We talked about this earlier. In this case, we have assumed that the lookup table is 10 bit wide, W equal to 10 in all these cases, red, green, and blue. That means what? We are looking at intensities of 2 to the power n, which is about 1024, 1 meg. Okay, 1024 possible intensities. Out of 1024 possible intensities of red separately, green separately, and blue separately. That means the darkest value of the red or any color up to the brightest value of a particular color, that entire range is now split into 1024 different quantum levels or discrete steps, is what you can imagine, from 0, 1, 2 up to 1024 minus 1 or 1023. So, out of 1024 possible values, where is this 1024 coming from? Well, W equal to 10, 2 to the power 10. So, that is the way it comes out. 1024 or 1k, I am sorry, I talked about 1 meg, 1k values. Out of those 1k possible values, which the which you can assign onto the lookup table, the programmer a priori chooses 256 or 2 to the power 8 possible values and loads the lookup table. Okay. So, you choose why 256 again 2 to the power n. As we look into the figure, 256 possible entries, but each entry 10 bit wide. Each entry 10 bit wide will be one color, red, green and blue, one color obviously, but the shade of that color will be 1 out of 1024 possible values, 2 to the power 10, 2 to the power w as we are talking. So, out of 1 out of 1024 values will be loaded into each entry of the lookup table, and there are only 256 such possible values in one lookup table, shades of red, shades of green and shades of blue respectively. So, these are the 3 different shades which we are talking about for 3 different reds, and now you can imagine these lookup table contents will be now passed on to the electronic gun. I could not put it all in one slide. If you look back into the slide again, it runs from the 24 bit plane to the if you recollect the picture which was just shown, then we are looking at 24 bit plane to the w bit wide lookup table. Okay. So, when we move to the next slide, it is a continuation of the previous picture. Okay. So, I hope you are able to see the next slide, and we are looking at a 24 bit plain color frame buffer with a 10 bit wide lookup tables, and for this yes, now you can see the picture. I will show the continuity of the picture. I will go back to the previous slide. So, we are looking from a 24 bit plain frame buffer to a lookup table, and from lookup table now we are seeing the remaining part of the picture, because if I had condensed these 2 into one picture, things would have been too small for you to visualize what is going on. So, this is a continuity. Okay. So, we stopped in the previous slide with the lookup tables. Now, the lookup table contents which is being addressed by the corresponding register 1 out of the 2 to the power n or 256 positions, one such content will be dragged out like a memory address, and then memory contents are taken out and it is passed on to a W bit wide DAC. Okay. W bit wide digital to analog converter, 3 DACs again for 3 separate colors R, G and B, or red, green and blue, and the DAC contents are again output to the corresponding red, green, blue colors, and they all converge to a single pixel, a triangular phosphor dot arrangement for RGB in a single raster plane. Okay. So, I hope this arrangement is getting clear. I will just roll back one slide back and forth for you to visualize the continuity. These 2 slides from one picture, basically we have taken this from the book by Rogers. So, we are talking from a 24 bit color frame buffer, and then we are talking about 10 bit wide. We have an n bit wide register sitting in between 3 registers for each color, 3 lookup tables for separate colors. Then from the 3 corresponding lookup tables, yes, the next picture is we feed it to the corresponding 3 DACs, each W bit wide. Then we have again the 3 color guns. 3 color guns generate the corresponding intensities. They all fire onto the CRT raster. Okay. So, this is the probably the last slide which we look in terms of CRT display monitors. To wind up the remaining part of the lecture on display devices, we may not come back to that again. I thought we had done extensively a discussion on CRT monitors, specifically do with the raster refresh, video scan, basic refresh rate, memory access architectures. We looked at the arrangement of guns, lookup tables and all that which is necessary, and those are the common display devices which are used, the monitor ones. Okay. And therefore, there are other types of display devices which I gave at the beginning about 3 classes back, and I think we must just touch upon a few points about the other modern days display devices which are coming out in terms of the consistently, as you see almost on the screen. The TV of course is a monitor based, but we started to having the LCD panels or the flat panels display monitors which are different. They have some advantages with respect to the CRT monitor. So, I thought we will wind up this discussion with a few points about LCD and flat panel displays. Okay. So, LCD or a liquid crystal display device is made up of basically 6 layers. The first of them is a vertical polarizer plane, then the second layer is a layer of thin grid wires, and the third is a layer of the liquid crystals which is in the heart or in the kernel or the center of the displays, and then again a layer of horizontal grid wires, then of course again a horizontal polarizer as the 5th layer, and finally a reflector. So, they are made up of 6 layers. The crucial part are the 2 polarizers and the layer of LCDs in between. I think that is what causes the LCDs to function. It glows or it becomes dark. Okay. So, the LCD material is made up of long crystalline molecules. Okay. So, when the crystals are in an electric field, they all line up in the same direction. So, there is some is more to do with devices and technology of materials. So, we assume for the time being we do not have much time to go into details for this course. So, touching upon it, LCD material is made up of long crystalline molecules, and the crystals line up in the same direction when an electric field is applied. Okay. The active matrix panel, that is also a term which is used for all these basically flat panel displays and also LCDs occasionally. Active matrix panels have a transistor at each grid point x comma y at each position, and crystals are dialed up to provide the color. So, you can have LCD color monitors as well, and the transistors basically act also as a memory, because they also cause the crystals to change their state quickly and hold on to that voltage till the transistor stage is switched back again. Okay. And the advantage of LCD displays, you can almost imagine they are there in your calculators and palm tops, desktops, and even on the controls of sometimes on TVs, air conditioners, handheld devices like cell phone, mobile units and all that. So, LCD displays are very low cost, they are low weight, they are small in size, and they have a very low power consumption as well. Okay. Continuing with that, the display contains 2 polarizers. In fact, we talked about 6 layers, and the task mainly is done by the 2 polarizers and the LCD crystals in between, and the 2 polarizers align 90 degree to each other. We talked of horizontal and as well as vertical polarizers, and with the display in its off condition or its off state, the light entering the display is plane polarized by the first polarizer. Okay. When the display is in off state, the light entering the display is polarized by the first polarizer. Then what happens? This polarized light passes through the liquid crystal sandwich. Okay. So, we are talking of layers in between, liquid crystals are sandwich, and then through the second polarizer and is reflected back to the display. So, in fact, when the display is off, the light is allowed to pass through these layers, pass through the first polarizer, the sandwich layers of crystals in between, and also to the second polarizer, which is if it is horizontal, then you have the vertical one, and the light is allowed to go and fall on the display, and we see the portion of the LCD illuminated. Okay, illuminated, or it is enlightened. Okay. Well, when turning the pixel on means it is done by basically applying an electric field, causes the crystal to untwist. Okay, the crystal changes its position or state, and that causes something else, because the light now passing through the liquid crystal sandwich is absorbed by the second polarizer. In the previous case, it was allowed to go through. In the second case, it is absorbed by the second polarizer, and the pixel starts to appearing dark. So, dark and light is what is controlled by the corresponding transistor or the electric field by switching the state of the crystal. Okay. In terms of twisting and untwisting it. So, that is the logic which you must just keep in mind. One has to study extensively about LCD panels by opening manuals and books to understand the technology behind it. Well, just again we are going into introductions of these. Basically, displays are of 2 types, plasma gas discharge and electroluminescent. We are talking of flat panel displays. They could be of 2 types. All flat panel displays are raster refresh displays. We talked of raster displays at length in terms of the CRT monitors or CRT monitors, and all flat panel displays are also of the CRT are like the CRT monitors, they are the refresh raster type. Okay. So, we continue, and a flat CRT, unlike the monitor where you have a big arrangement of the electronic gun, the anode heating element, and then of course the horizontal deflection plates, control grids, focusing unit, either electromagnetic coil to reflect the voltage or analog or deflection plates, horizontal and vertical, and then the beam courses through the shadow mask, has to fall on the phosphor coated screen and dots. All that of arrangement makes the CRT look very big. You can see the TVs are the monitors with the CRT. If it is inside a CRT, it has to be big and voluminous because of this, and there are other problems because it increases the weight of the system. There is heat generation wherever it works, and also it occupies space, volume and all that. Okay. A flat CRT has a very big advantage that it is sleek because and flat, because the flat CRT is obtained by initially projecting the beam parallel to the screen and reflecting it to 90 degrees. So, typically when you are watching a screen, a flat panel, the Unlike the electron beam for a CRT monitor, which just directly goes almost perpendicularly to the phosphor screen and then is deviated and impinges on a phosphor dot on the screen, it is the other way around, that the beam is basically running almost vertically along the screen and then diverted and hits the particular point on the screen. It is reflected and by 90 degrees and hits the screen. So, that is the advantage of why it is sleek. Reflection of electronic beam, it is done by, of course, optical devices, electro-optical devices, reduces the depth of the CRT bottle and also the display. Okay. So, that is obvious, and the plasma display, like the LCDs, are also active matrix displays. Okay. They are also called the active matrix displays here, and the required voltage or current to control the pixel illumination is supplied using a thin film transistor or diode. That is a technology which is used to control the pixel illumination. We require, because you need to control the intensity also there, correct, along with the color. So, that is done by a thin film transistor or diode. Okay. So, this brings us to the end of the lectures on CRT display devices. We had a sequence of 4 hours of 4 classes or 4 lectures, and we have discussed extensively about CRT monitors, because that was the basic target. You should know about the technology, and we touched upon a few points about LCD panels and flat panel display monitors. There are other types of output devices, of course, which we may not touch. Input devices like the keyboard and the mouse we talked about, and of course, output devices like plotters and printers and all that. But with respect to the time allotted, I think I will move over to algorithms and other concepts on graphics, and you have to bear with me that I could not talk at much length about other interface and other input output devices used in computer graphics, and I spend most of the time on CRT display devices and touched upon flat panel devices. Well, I have made at the end of each lecture a set of questions which you should try to solve it yourself, answer yourself, and even there are some problems given in each of these, and they will be shown at the end of each slide. And please go back, learn more from the books and references which have been quoted in the introduction slide, and try to solve these problems. Yeah, although we said that you could solve all the problems at home, we will discuss a few selected set of problems right now, and we will choose one problem from each particular task. So, kindly choose one such problem from the take home task 1.
Can we discuss task 1 4th problem?
Yeah, that is nice. That says that the average time to execute an instruction in the display list is about 33.3 microseconds, and if the frame rate is 30 frames per second, the problem says obtain the maximum number of instructions that may be present in the display list for random scan displays. If you remember, random scan displays was basically a line drawing display device, and it had in the display list a set of instructions. So, it is a sequence of instructions which are basically executed one after the another, and we want to find out what is maximum number of instructions which could be placed. So, to solve the problem, let us come here. The problem says that we have a frame rate of about 30 hertz, that is the frame rate, and from that we can easily obtain the time to scan one frame, correct. The time to scan one frame multiplied by the frame rate, or that is the number of frames per second, FPS or hertz, it gives 1 second. So, time to scan is 1 by that value, which is 1 by 30 seconds or 33.3 milliseconds. 33.3 multiplied by 10 to the power minus 3, that is engineering unit, milliseconds, and hence since the problem states that the time to execute an instruction is only 33.33 microseconds. Okay, so that is 10 to the power minus 6 unit here, and time to, you have actually 10 to the power minus 3 unit here for one frame. So, total number of instructions should be this divided by this. So, 33.3 cancels out, and the answer is very easy. You can obtain that, you can actually put 1000 frames per second. So, that is the very easy to compute. The answer is 1000 microsecond. Let us go to another question.
Sir, can we discuss task 2 third problem?
Task 2 third problem, that is good. Well, you see that this is something to do with the resolution of the screen. If you remember, when we are talking about resolution of the screen, there are concepts of frame buffer, bandwidth and scan rate and things like that, but the actual resolution which is there on the monitor, it depends on the pixel size, physical dimension of the pixel size. So, let us look at this problem. So, that is where in this case although this problem is very easy, we said that let us say if you have a video monitor where the size is 12 inch in width and 9.6 in height, okay, and we had said that along this we have 1280. Okay. So, we have basically want to put 1280 pixels along each 1280 pixels along each row, okay, and each row will be 1280 and the total number or 1280 columns, basically 1280 columns, and the number of rows is 1024. So, there are 1024 rows and 1280 columns of pixels. That means, the row width is basically 1280 and the height of a column is 1024. So, either way we can visualize it, or you can also say that the number of columns is 1280, number of rows is 1024. That means, each pixel, I have a small pixel here, that is it is arranged in, we assume that for the time being that they are arranged in the form of a matrix, okay, and there are 1280 such thick in the horizontal direction, x direction let us say, and in the y direction 1024, and the question is how many such pixels we can pack. It depends upon the physical dimension, and so number of pixels multiplied by each unit gives this. So, we can say that if each such unit is of width w, each is of width w, then we will say w multiplied by 1280 gives you actually 12 inches, and which in turn basically tells you that w, that is the width, will be actually 12 inches by 1280. Okay, that is very simple, and that answer is about 9.4 multiplied by 10 to the power minus 3 inches. Okay. So, that is the, you can actually get this value also by dividing 9.6 by 1024, correct. You will also actually get this value, you can feel for yourself that is almost close to 1000, 9.6 here. So, the value will be little bit numerically less than 9.6, it will be 9.4 into 10 to the power minus 3. So, that is the width and the height for each individual pixel. So, that is the way you compute the size. Okay. Let us go to the next
So, in task 3, can we discuss the first question?
Task the first question, as said here, we are asked to compute the refresh, we are asked to compute the access time for each pixel for systems which have two different resolutions as given there. One is 640 multiplied by 480, the other is 60 and 1280 by 1024 is the other resolution, and the refresh rate is 60 frames per second. So, let us take task 3 and problem 1, and we are taking off a resolution A. So, we are talking of a resolution which is 640 multiplied by 480, that is the image resolution or screen resolution also you can say. I will better put it as screen resolution. Okay. And we are talking of a refresh rate of 60 hertz or 60 frames per second. I did teach you that you can use these terms interchangeably. Hertz means per second or FPS is frames per second. Okay. So, if that is the frames per second. So, time to scan, time for one frame scan, or basically meaning scanning one frame, time required to scan one frame, I write it as time for one frame scan is basically 1 by 60. Okay. How much 1 by 60 comes? Okay. It will come an about 16. about 16.7 milliseconds. Okay. You can check it out yourself, it will come to about approximately 16.67 or 16.7 milliseconds. Is that correct?
16.67.
16.67, I round it off to 16.7. Okay, that is good. Okay. Now, we are talking about, so in 16.7 milliseconds it must access so many pixels. 640 multiplied by 480 pixels must be accessed in 16.7 milliseconds. So, time to access 1 pixel. Is actually, you can take this 16.7 divided by 640 multiplied by 480, so many milliseconds. Okay. If you divide this and compute yourself, you can check the answer, it should be 50, it will come to about 54 microseconds. It will come to about 54 microseconds, 54 microseconds. Now, this value of 54 microsecond includes actually the time for vertical retrace. That means, individually accessing all the pixels from left to right per row, and then for second row, third row, and all that, and then you need to have time for retrace, both horizontal and vertical retrace times. Actually, if you take into account that time, which typically takes about 17%, about 17% of the time, then you will be left over with about 0.83 of the time. So, this value of 54 microseconds will actually, you need to probably put a multiplying factor of about 0.83. Okay. So, assuming 17% of the time is gone for retrace per frame in out of the 16.7 milliseconds. So, you will be left over with 0.83 of that time. If it is 15% for retrace, then you will have 0.85. Okay. So, that value goes down by some amount. It will typically, you can calculate for yourself, 54, it will come to about 42 microseconds or so. You can check it out yourself, how that the value is. Can you check that out? We can check it out right now. Yeah, it comes to about 45 precisely, about, you can round it off, the value comes to about 45 microseconds. So, that is the part A of the problem, and I will overwrite in a similar way the part B says that the resolution is increased. The resolution is increased to 1280 multiplied by 1024. So, we will move into the second part of the problem of task 3 problem 1, where the resolution now is 1280 multiplied by 1024, keeping the refresh rate per same, time to access per 1 second is also same. Okay, and we keep that factor of 0.83 here. Okay. I think I can rub it off and write again neatly. So, I will say that 0.83 multiplied by 16.7 milliseconds divided by 1280 multiplied by 1024. Okay. You can have a calculator yourself, you can check it out. It comes to 10.5. It comes to, now you can see that the bandwidth requirement is probably so large now. Okay, it is already and this is the time to access per pixel. We talked about bandwidth requirement now, where within this time to access per pixel it has to go on, the beam has to go switch on, switch off. So, we are talking about almost about 5 microseconds of access time. We are talking about almost about the bandwidth requirement of 1 MB, 1 megahertz type of bandwidth is what you are requiring at this. But of course, there are higher resolution monitors also available, higher frame rates, and you can start to visualize that the amount of time in which the beam has to switch on and switch off, access a particular pixel will be still going down further and further. Okay. Yes, can we discuss some other problem? We just have time.
task 4 first problems.
Yes, that is a very interesting problem. Task 4. Problem 1, thank you. Assuming a transfer rate of 0.1 megabyte per second. So, we are talking about a transfer rate of about 0.1 megabyte per second, which I will almost take it approximately equal to 100 kilobyte per second. It is not true, but it is an approximation. 1 meg is about 1024. So, it should have actually come to 102 kilobyte per second. You can actually take that, and then how much time would be necessary to load PixMaps with resolution. So, the first problem talks about 512 multiplied by 512 into 1, so many bits. It is in bits, that is in bytes. So, to transfer this into bytes, I must divide it by 8. So many bytes have to be transferred. Okay. So many bytes have to be transferred, and the rate is known as 100 kilobyte per second. So, if you calculate this, you are basically the time taken requirement. So, in 1 second or 100 kilobyte you can transfer in 1 second. So, this actually comes to you can calculate yourself, it comes to about 32. This is actually about 32 kilobytes. You can check it out yourself, because this 512 divided by 8 will actually give you 2 to the power 5 or 2 to the power 6. So, you will have 2 to the power 5 here and one term going here to take care of the kilobytes. So, 2 to the power 6 is what you get. You basically get 32 kilobytes you need to be transferred, 100 kilobyte in 1 second. So, in 32 kilobyte the time required will be about 0.31 seconds, 0.31 second. Okay. So, that is the answer for the first part. I will quickly override the answers with the second part. If I say the second part, that is the part B, has 1024 and 1280, that is the large, more or less the larger monitor. 1024 multiplied by 1280 divided by 8. So many bytes have to be transferred, and this typically goes to about you can check it out for yourself. Actually, it will come to about 157 kilobytes. Okay, check that. You have to basically transfer the bytes to kilobytes. You can compare. If in 100 kilobytes you can transfer in 1 second. So 157 kilobytes you need. The answer is very easy, 1.5 seconds. So that is the answer. That is the answer. 1.5 second is the answer which I have. Okay. Thank you much. You should try the rest of the other problems which are given in the take home tasks. Thank you very much.